you very much. So first of all, I would like to thank the organizers for the invitation. And so I will move the slides with the. So today I would like to tell you something about dynamics and localization in polar lattice gases. So this is pretty much related to the talk of Silke, and also to the talk of yesterday of Giovanni Modugno. So I was not here in the talk of Giovanni, but was surely talking about dipolar gases. So dipolar gases, I don't need to introduce this too much because, as I say, this has been done already in the previous talks, are systems in which particles interact significantly or even dominantly via dipole-dipole interactions. So either magnetic dipole-dipole interactions in the case of dispersion experiments, like it is the case, or erbion or chromium, like it is the case in the experiments of Giovanni, for example, or electric dipoles, like is the case, for example, in the polar molecules experiment that Silke perhaps was mentioned. So this is an interaction which occurs like 1/r⁻³ and is anisotropic. This changes the rules of the game, and this changes pretty much the physics compared to the non-dipolar counterparts. This has been shown very spectacularly, so to say, in experiments with dipolar Bose-Einstein condensates, and in particular in the recent series of experiments in the group of Giovanni, in the group of Francesca Ferlaino in Innsbruck, and in the group of Tilman Fau in Stuttgart, always with magnetic dipoles. But today I would like to tell you a different aspect of the physics of ultra-cold gases, ultra-cold dipolar gases, which is what happens if you put them in an optical lattice. So when I will consider that these particles are confined in a deep optical lattice, such that they are in the tight-bending regime, and they can be considered an instance of what is called an extended Hubbard model. And for the rest of the talk, I will just concentrate in the one-dimensional case. So here, particles can move via hopping to the nearest neighbor, to the right or to the left, in the case of one-dimensional systems. They have on-site interactions and they have inter-site interactions. And this is the new ingredient that you have in extended Hubbard models, right? In the usual Hubbard models, you just have these on-site interactions. For the case of Bose-Hubbard models, this is the Bose-Hubbard. You have some inter-site interaction, which may have also next to nearest neighbors, next to nearest neighbors, and so on. So they decay with some power, which you typically assume to be 1/j⁻³ 1/distance to the power 3, simply because the dipolar interaction goes like 1/r⁻³. Also, this is something that we will revisit at the end of the talk. So the ground state physics of these systems is known and is very rich. You don't have only just the multi-insulator and the superfluid, as you have in the usual Bose-Hubbard Hamiltonians, but you may have other type of phases, like different type of crystalline phases, lattice supersolids, so-called Haldane insulator, and many more. The experimental situation is much more modest, despite of some experimental breakthroughs, in particular in the group of Francesca in Innsbruck, on extended Bose-Hubbard Hamiltonian using erbion atoms. In this experiment, they enrich to this ratio between the interstate interaction and the hopping of the order 2 to 3, which is actually this ratio P/T is the figure of merit, and it will appear many times in this talk. But there are other interesting developments, and some of them have been commented today in the morning by Silke at the end of her talk. The fact that you can shield your system against inelastic collisions opens actually optimistic perspectives for the study of Hubbard models with polar molecules. There is, of course, other realm, which was mentioned by Silke also, which is the simulation of spin models. So models in which the particles do not move, but we have been working quite a lot on that, but I will not discuss this here. I will concentrate actually in the motion of particles. So, and I will actually focus in the specific case on the specific case of hardcore systems, so systems in which you have an occupation of 0 or 1 particle. So, and actually, many of the things that I will mention are also valid for the case of fermions. And so this is for the case of bosons. You get it if you have an on-site interaction which is sufficiently strong such that you can safely outproject states with occupation larger than 2 or equal than 2. So, and I will concentrate in the particle dynamics, not in the ground state physics. So I'm interested in how the particle dynamics occurs, and we will see that the combination of several things is making these dynamics rather intriguing. So you have on one side the energy conservation, which is very good in this type of system. They can be considered to a very large extent like isolated systems. You have the discreteness, so basically you just move to the right, to the left, one by one. And you have also related with that, of course, the finite bandwidth of the system. And this is very important, of course, for this type of systems, you have these intersite interactions and the tail of the intersite interactions, which will play a non-negligible role and actually a very important role as well. So, in order to illustrate this, because before I pass to the bulk of the talk, let me just, as I say, illustrate this type of dynamics that you can have in the system with the particular case of dimers. Yes. So let me just consider an initial situation, yes, in which I create by initial condition, just because I want, two particles in neighboring sites. Yeah, so they form, so they are at neighboring sites, and they are interacting with an energy which is this intersite interaction to the nearest neighbor V. And if I try to move this particle to the neighboring site, then I have to break this pair, and so I have to pay the energy penalty V, and the energy is T for this motion. So if T is much smaller than D, then this pair cannot be broken, but can still move in second order. So I can move first this particle and then the other one with an overall hopping T square over V, of the order T square over V. This is nothing new. This is very similar to what you have in the so-called repulsively bound pairs for on-site systems. So for the usual Hubbard models, not extended Hubbard models, where you have also this the formation of this pair both for bosons and for fermions, and this was actually studied experimentally several years ago. But the difference with this system is that here there is a small energy scale that competes actually with this hopping, which is the dipolar tail itself. And the best way to see this, yes, is if you consider a dimer gas. Suppose that I create a set of dimers in my system, right? And I let them evolve. And I ask myself whether they will move or not. Now, this, as I say, these dimers now move correlatedly, so they move via this second order hopping, but they also interact with each other at a distance like 1 over L to the power 3 in this type of model. And this means that if the energy associated with the motion of this dimer, which is this dimer hopping, is smaller than the energy that you gain or you lose when you move towards this one or in the other direction, right? Then this motion is non-resonant and you don't perform this motion. So basically what happens is that for distance and more, initial distance is more than a critical distance, this is the result of this four-body problem, you get a bound dimer-dimer cluster. So basically what you get is a repulsive bound pair of repulsive bound pairs, basically. And you can imagine that now the only way that this moves is in fourth order. So you can imagine that this actually leads to basically quasi-localization of, for any practical purposes, localization in dimer gases due to this dimer cluster formation. So you can see that already from this relatively simple example that the effect of the tail may have, at least for some states, a strongly localizing effect, so to say, and can make the dynamics very slow, and even you can get localization in absence of any disorder with this problem. And this is linking now. This is bringing me now to the main point of this talk, which is how the link of this with recent developments in what is called many-body localization without disorder. So by now it is more or less understood that very few conserved quantities may result in non-electricity of your system in absence of any disorder. Yes. So this is because of the appearance of the dynamical constraints, which basically fragment your Hilbert-space into regions, into sets of states which could be in principle energetically connected with each other, but they are not dynamically connected because there is no path to go from A to B, so to say, from one state to another state. A good example of that is the so-called Stark localization. Yeah, so basically you put a system in a tilted optical lattice with and actually there have been some very nice recent experiments in Munich by Monika Edersburger and also in ions and other systems. So this idea of Hilbert-space fragmentation will play a very important role, and the idea of dynamical constraints in the analysis of the dynamics in polar lattice gases. And in order to see this, we should basically disentangle the different ingredients that we have here. So I will discuss first of all what happens. I will discuss first what happens with system with just nearest neighbor interactions, and then we will add the effect of the tail of the dipolar interaction. And then at the end of the talk, I will discuss what is the actual tail of the dipolar interaction and why this matters. So let's consider first the case in which I have just nearest neighbor interaction, so purely nearest neighbor interaction. Now you can imagine that if this d is much larger than t, right? So if you are in this region, now this quantity of here, which is the number of nearest occupied nearest neighbor links, becomes a conserved quantity, better and better conserved. So this is this emerging dynamical constraint that you have in the problem, right? Which will limit your dynamics. Now, indeed, as a result of that, you get a Hilbert-space fragmentation, which you can visualize in a very nice way. If you have a look to the focus states and you express the focus states in the basis of eigenstates and you properly order them, which I did it here for you, then you see basically the appearance of these boxes here, right? So basically you take a focus state in this box, right? It will just connect with focus states within this box. So basically you fragment your Hilbert-space in regions of states which are connected to each other. And these are not just blocks with a given number of nearest neighbors, but you have also a sub-block structure, so to say, of states which may be dynamically connected even for an infinity of time. Right? Even for short times, this fragmentation is even stronger. Strictly speaking, Hilbert-space fragmentation in the case of nearest neighbor interactions do not lead to many other localization without disorder. And the reason of this is this very simple mechanism. So suppose that I give you a cluster of, let's say, 4 particles in a row. Now, if this is alone and V is infinity, this guy doesn't move at all, right? But now suppose that there is this lone guy here, which I will call a singlon, which approaches now to the next nearest neighbor here. And now I can have a row of resonant processes, like this guy moves here, this guy moves here, this guy moves here. All this conserves the number of nearest neighbor links, and now this guy moves apart. So as a result of that, the singlon and the cluster swap positions, but you see that this cluster has experienced like a recoil, right? And this recoil basically eventually may delocalize clusters of any length, this type of process. Of course, this as I will comment later on, if you have a system with periodic boundary conditions and so on, basically these singlons can go around and delocalize. But if you have a finite system, this mechanism can be quite inefficient, and I will discuss this in a second, because this is important for actual experiments. Now, let's move to the second ingredient, which is the tail of the dipolar interaction. Now, if you have the tail of the dipolar interaction, and I still consider this tail as 1 over j to the power 3, now you see that when you increase the ratio V over T, then you don't only enforce more and more of the conservation of the number of nearest neighbors, but you start to conserve other quantities. You start to have additional dynamical constraints, starting with the conservation of the number of next to nearest neighbors. And actually, just the conservation, this emerging second constraint is enough to shatter the Hilbert-space. So basically, what I had before, this type of block structure, now I have a much more diagonal configuration here. So this means that I have shattered basically this structure. And indeed, you can study the shattering. Yeah, so you pass from this distribution for nearest neighbors to something which is much more diagonal. This one in this 1 over j cubed model. So basically, you can have a look to the inverse participation ratio in this in the basis of eigenstates for each focus state. You compare the inverse participation ratio with the size of the block in the nearest neighbor model in this logarithmic way. And then basically you average over all focus states, and this will give you a relatively good idea, quantitative idea of how much do you fragment these blocks, how much you shatter them. And indeed, when this number tends to 1, this means that this fragmentation is very inefficient. When this tends to 0, this means that you have exponentially destroyed, basically. You have destroyed these blocks and basically get into a diagram. And indeed, you get a sort of here, this for relatively small systems, because actually you cannot do much more in this kind of system, because you have to make the whole Hilbert-space. But you see this type of basically this type of crossing here at 20 roughly, which is marking this shattering of the Hilbert-space, basically from the nearest neighbor blocks into a shatter structure, just because of the presence of the next to nearest neighbor interaction. This has, of course, consequences for the dynamics, right? The motion is going to be much more localized because the presence of the next to nearest neighbor conservation prevent the resonance swaps, which are where the mechanisms which were delocalizing clusters. Also, you have formation of non-local clusters, and in general, the dipolar tail will favor localization. So let's have a look to how this really works in finite systems with open boundary conditions, or really what you will have in an experiment. Because as I told you, this mechanism is relatively inefficient. Yes. And the reason is because every time a synchrone goes by, you will recoil, right, by 2. But in order to delocalize this in a lot of states, in a lot of sites, you will have to have many synchrons, basically, to go basically across all the time. And this means that, and this is, by the way, what I will say here is not just a finite size idea, so to say. It's generally true if you don't have enough synchrons compared to the number of clusters that you have in the system. So, so the typical thing that you will have is something like this. So let me just go quickly to what I am showing to you here. So basically, what I will do here, what I do, is to consider all possible focus states, all possible initial focus states that I can have in my system. So I consider all possible initial configurations of particles, let's say 1, 0, 1, 0, 1, 0, blah, blah, all possible configurations. For this particular case, the only constraint is that I have like half filling, and let's say that the initial number of nearest neighbor links is 1/4 of the number of sites. And then I do just the statistics of this so-called inhomogeneity. So this is basically a number which is 1 in a focus state, which is maximally inhomogeneous, and 0 if everything is homogeneously distributed, right? So if you, now I let my system start with some initial condition, I let it evolve during some time, and I calculate this inhomogeneity. I do it for many of these, and I do the statistics, right? And this is basically for relatively large interactions, and this is the time in a logarithmic scale, which is a very long scale. This is for the nearest neighbor model, and this is for the 1/j³ model. So you see that even in the nearest neighbor models, you have this residual inhomogeneity, right? Because of this inefficiency of this resonance swapping. But you see, of course, that you have much enhanced, so to say, basically to a very large extent localization in this system, because you see that inhomogeneity is very, very large. Now, if instead of having a large value of U/T, now you are below this shattering, which was around 20, then the residual inhomogeneity in the nearest neighbor model, for example, for 5 is relatively large still. But you see that if you wait, let's say, for a very long time, the 100 hopping times, you see that the dipolar tail, actually, this 1/j³ tail, is helping you to delocalize. And the reason is because it's helping you to bridge these energy gaps, basically, which were preventing the breaking of pairs, like the breaking of timers. So indeed, if now you study for a fixed time, then you have this type of, as a function of d/t, you fix the time, like 1,000 hopping times in this case. So this is the nearest neighbor case. Basically, this is the average value, and this is the variance, right? In the this inhomogeneity parameter. And you see that you go from 1/r³ induced delocalization to a 1/r³ induced localization, and basically the border is around the shattering transition. So, and now let's go to the last ingredient of what I want to discuss, which is this tail really a 1/j³ tail, and does this matter, right? And as you can imagine, what I will tell you is that many times this is not really the 1/j³. But in order to discuss this, we have to go one step back and see how do you actually generate a one-dimensional system in typical experiments. Because there are 2 non-equivalent ways of doing it. One is that you put the system in a 3-dimensional lattice. The axial lattice is much weaker than the transversal lattice, and then you basically split your system into individual rows here. Where you forbid the hopping, because this is very, very large. You forbid the hopping between rows. So you have one-dimensional system In a dipolar system, by the way, you will have to empty sites around because despite the fact that you have hopping, you will have still an effect of intersite interactions with the dipole. The other non-equivalent way is to have a one-dimensional lattice and confine it harmonically in the transversal direction, right? And as we will see, these two things are not equivalent, and not equivalent in general. In both cases, you will generate a model like the one that we were discussing before. But now the question is, what is going to be this V over J? And this is actually the result of this type of integrals, basically, where this is the dipole-dipole interaction. Here I am considering a given angle between the axis of the lattice and the dipole, but this is not so relevant. The important thing is, what are these wave functions, which are the on-site wave functions associated with the lattice? These wave functions are, if you consider a transversal harmonic confinement, they are transversally, this is the wave function of the transversal harmonic oscillator, the ground state, with a given harmonic oscillator length. And actually, you have the Vanier function, which for a sufficiently large, sufficiently deep lattice, you can approximate doing the harmonic approximation, at least in what concerns the calculation of interactions, right? Interaction terms, by, as I said, you can approximate it by a Gaussian, where the width of the Gaussian is given basically by the wavelength and by the depth of the lattice in units of the recoil. This is the typical way of typical notation in the lattice business. And this is the recoil energy, which is basically the energy associated with inverse wavelength in the square. Now, for the case of a three-dimensional lattice, the situation is going to be the same, right? Because for the three-dimensional lattice, I will have the Vanier function in the three directions, but as I say, in the transversal direction, the confinement is even stronger, so to say. So it is even better to use the harmonic approximation. So basically what I have is a Gaussian in the transversal direction with a given width and a Gaussian in the axial direction with a given width. And now this aspect ratio plays a crucial role because, and this helps us to understand why these two things are not equivalent, because now here, by definition of the fact that this has to be very strong in order to prevent hopping, this ratio is much smaller than 1. So the transversal direction is much smaller than the axial direction. Whereas in this case, under very general conditions, the typical situation is actually that your transversal direction is going to be weaker. The transversal confinement is weaker than the axial confinement. So basically, the axial extension is smaller than the transversal extension. So you are going to go from functions which look like this to functions which look more like a pancake in this case. If you have a look to how these functions look, so how these integrals look under this pancake condition, funny enough, you can do this analytically. So you get basically a constant, and this constant depends on the dipole and so on. But what is more important for me for the discussion is the fact that you have the tail of the dipolar interaction, which follows some function here, right? But the tail of this interaction, this is my point here, depends on a single parameter, which so the tail of the dipolar interaction, whether it is going to be at the end of the day like 1 over j cube or going to be something different and so on, is universal in this parameter. And this parameter is something very physical because it depends on the ratio h bar omega perp over the recoil. So it's basically telling you how strong you confine in the transversal direction. And it depends also on the lattice depth. So this means now that in the case of 1 over j cube, the physics is universal in d over t. So once you eliminate this overall energy scale, which is given by the hopping, everything is universal in d over t, and this is the reason why I was showing to you all the graphic before with d over t. But in an actual dipolar system, the physics is universal in 2 parameters, in d over t, and in this other parameter. So basically, everything can be universally given by that, where v over t characterizes the interaction strength, and b characterizes the actual decay of the interaction. And this decay of the interaction may be significantly different than in the case of 1 over j cube. Yes. So this is, for example, for this particular parameter, which I put here some numbers. Yes, for example, for sodium potassium molecules and 500 nanometers of this is a relatively even strong confinement, like 1.6 kilohertz in the transversal direction. So this is the result, or this is this exact interaction, and this is the 1 over j cube. Now, the most interesting thing is what happens at next to nearest neighbors, because as I told you, is the next to nearest neighbors basically what plays the key role in the Hilbert-space fragmentation, the dynamics, and the localization. So now I will parameterize this actual value compared to this value by this exponent, this sort of effective exponent. I'm not saying that that everything will decay like this exponent. I'm saying that the next to nearest neighbors is going like 1/2 to the power beta. Yes, it's not like 1/8, but for example, in this particular case, is 1/4, right? Because this is for this particular case, you have 1/4 and not 1/8, which is what you have here. So, how does this beta go? Now, this beta, as I say, is a function of this b, but if I fix the lattice depth, it's basically a function of the transversal confinement. So if your transversal confinement is very strong, this means that L per is smaller than L, and this is what you have in these three-dimensional lattices. This power actually goes to something very close to 3. It's a little bit larger than 3, but if the lattice depth is sufficiently large, it's very close to 3. So this means that the result that I was telling to you about with 1/j to the power 3 should work relatively well in the typical three-dimensional lattice. Now, what happens if you are here? Now, if you are here, yes, now the situation is maybe potentially very different, right? Because if your confinement is sufficiently small, and sufficiently weak in the transversal direction, and as I gave to you the example before with sodium potassium molecules, doesn't need to be actually very weak, maybe even strong. To finish. So you can get powers which are significantly smaller. And the question is, does this matter? Yes. And this matters, as I will show you quite a lot, because as I told you before, the Hilbert-space fragmentation and the localization depends very much on the ratio between the next to nearest neighbor and the nearest neighbor interaction. So if you have a look now to the Hilbert-space shattering, you may do the same analysis that I told you before, taking the inverse participation ratio, calculating all these so-called fractal dimensions and so on. And here I plotted, in order to make the comparison, the case, so this is beta, and this is v/t, and this is for a model which is purely 1/j to the power beta, so really going all the way with 1/j to the power beta. And here is for a polar lattice gas with this exact dependence, but assuming that the interaction to the next to nearest neighbor is parameterized by this 1/2 to the power beta, right? So and this is this beta effect that I'm putting here. And you see that, and this is the shattering border, right? And you see that qualitatively and to a very large extent quantitatively, they are very, very, very similar. So this means that this system, the actual system, behaves like, at least in what concerns the Hilbert-space shattering, as a system with an effective power law decay that you can control with the transversal decay of freedom, with the transversal confinement. Moreover, something that is also important is that whereas for beta equal to 3, you have the shattering around 20, here you may get shattering around a much smaller value like 10, right? So your system is going to be much more prone to localization in the actual dipolar gas than what you think for the 1/j to the power 3. And as this is the last slide. So, and this has consequences for the dynamics, as I say, this is a very similar graph as what I showed before. So basically, again, I assume all possible initial Fock states and calculate this inhomogeneity after a given time. And this is the average, and this is the variance. This is in blue is again the nearest neighbor. In orange is the 1/j cube, and this green one here is basically the actual dipole with this decay, assuming that the interaction to nearest neighbor is 1/4, so 1/2 to the 2. And here you cannot see it because it's really on top of this one, is the actual 1/j square model. So really this behaves, right? Not only the average, but even the variance, so to say, it behaves really like a system with 1/r squared instead of like 1/r. So this means that the dynamics resembles very closely that of a 1/j to the power beta model, where beta is something that you can control with the transversal degree. So with this, I would like to finish. So we have seen that I have given you some examples. I didn't tell you all the history. I gave you at least some examples about how these dynamics in isolated systems, due to the effect of the tail of the Dipolar interaction, could be rather interesting and lead to localization in absence of disorder and Hilbert-space shattering due to these emerging dynamical constraints. And we have seen that the actual interaction tail depends on the transversal confinements and differs from the typical one of an acute dependence in a sort of universal way given by the transversal confinement. And as I say, the Hilbert-space fragmentation and the dynamics are to a large extent as in a system with a power law decay, where the power law can be controlled with the transversal confinement. This is what one is expected to see in actual experiments, right? As I say, you do it with a three-dimensional lattice, typically you would see something like 1 of j to the power 3, but if you do it with a transversal harmonic confinement, the history may be quite different. So with this, I would like to finish, not before thanking the people who has been contributing, Xiaolong, Weihan, Arya, and Henning in Hanover. Xiaolong and Arya have already left. With Kenichi and Luca, we work in this dimers that I was just barely mentioning. And with Kuba Zakrzewski, we are working in this last part that I was discussing. Thank you very much.